In this video, we're continuing our discussion of different methods for solving ordinary differential equations. So as you recall, we're going through solution methods for initial value problems. And in this video, we're going to discuss the midpoint method. So similar to Hume's method, the midpoint method provides a slight modification to both the implicit and explicit Euler methods. So consider again our initial value problem, dx dt is equal to f of x and t. If we assume that the value of the dependent variable x is known at an initial value ti, then we have the expression here. So we can integrate both sides of this equation. So evaluating the integral on the left, we have xi plus 1 minus xi is equal to this integral of f of x and t. Now we can use the midpoint rule of the rectangle method of numerical integration, which we discussed in the previous chapter, over one interval to evaluate this integral on the right-hand side. So doing that, we obtain the expression shown here. So we've got xi plus 1 minus xi is equal to h evaluated at, or times f evaluated at the midpoint between xi and xi plus 1. And the midpoint between ti and ti plus 1. And this locally had an error order h cubed. So the error term is inherited from the use of the I2 integral, or in the rectangle rule for a single interval. So the estimate for xi plus 1 is given as shown here, so just bringing our xi to the other side of the equation. And this is the expression for the midpoint method for solving initial value problems. So using this estimate, the local truncation error is proportional to the cube of the step size. And when we add the errors from each interval together, the total error is order h squared for this method. So this is similar to Hume's method and better than both the implicit and explicit Euler methods, which both had order h. So we can note here that the midpoint method is essentially a slight modification to the Euler's method, in which the slope used to calculate the value of xi plus 1 at the next time point is the slope at the average point, xi plus a half, which we can be defined as xi plus 1 plus xi divided by 2. So similar to Hume's method, the midpoint method can be implemented in two ways. The first is to use the slope at xi to calculate an initial estimate of our xi plus a half, and then the estimate for xi plus 1 is calculated based on the slope at our initial estimate of xi plus a half. Alternatively, we can use the Newton-Raphson method or another root-finding method to solve directly for xi plus 1. And similar to Hume's method, here we're only going to adopt the first approach, calculating this intermediate value. So the midpoint method is another example of this predictor-corrector approach, where the predictor equation gives us our initial estimate of our xi plus a half, which uses the explicit Euler method to evaluate this, where our function is evaluated at what we already know, so xi and ti, and then the corrector equation uses this estimate to find the next time point xi plus 1. So let's look at our same example that we looked at before, this time using the midpoint method. So again, consider this nonlinear initial value problem, dx dt is equal to tx squared plus 2x, with the initial condition that x of 0 is equal to minus 5, and we want to find the values of x for t goes from 0 to 5, with h is 0.1. So the midpoint method is implemented by first assuming an estimate for this x at I plus a half based on the explicit Euler method. So here we're finding the value of xi plus 1 half is equal to xi plus h over 2, because we're only considering half the step size, times dx dt evaluated at what we know, which is xi and ti. And then we find the estimate for xi plus 1 as shown here. So xi plus 1 is equal to xi plus h times dx dt evaluated at this midpoint xi plus a half. So with all of our values, we can plug this in to the first equation where xi, or x at 0.5 is equal to minus 5 plus h over 2 times t0 x0 squared plus 2x0. So plugging in our values, we find that x at 0.5 is equal to minus 5.5. And then we can use this information to calculate the slope at x 0.5, which we can use to estimate x1. So we plug in this value here for x 0.5 superscript 0, and here. And then here we're using t of 0.5, so that's just half the step size. So our t at t 0.5 is equal to 0.05 because our step size, or our h, is equal to 0.1. So plugging in all of our values, we see that x1 is equal to minus 5.949. So looking at the next time point, we find this intermediate value, x of 1.5, given as shown here. So where we're evaluating everything at x1 and t1. And plugging in our values, we get that x 1.5 is minus 6.3667. And we can use this information to calculate our estimate x2. So here we're evaluating things at t of 1.5, x 1.5 and x 1.5. So I'm putting in this estimate here. So we get that x2 is minus 6.614. And we can proceed iteratively to give the values of xi up to t equals 5. And this is the output of the MATLAB code using the midpoint method. And you can see that with a step size of 0.1, we get a very good estimate of the actual response for this example. And again, we can compare with the explicit Euler method. So the midpoint method behaves very similarly to Hume's method. And it performs much better than the explicit Euler method in this area where the function varies rapidly. And this makes sense since we know that the accuracy of the midpoint method is order h squared, where the explicit Euler method is just order h.